I'm going to run you through different solutions to the Chapter 8 review. You certainly don't have to watch the entire video. If there are problems that you already knew how to do, just skip to the ones you don't know how to do. I do have this linked on Schoology, so you should be able to see the original PowerPoint. I would suggest you just do the PowerPoint, maybe number it or kind of do your work, kind of run through it, and then you can pick up and take a look at the video and you can see which ones you need to see again. All right, so our first question here, true or false? All equilateral triangles are similar, okay? So remember, we've got different options for proving triangles similar. We've got the angle-angle rule, we've got the side-angle-side rule, we've got the side-side-side rule. This one can actually be shown a couple of different ways. First of all, if you just start trying to draw triangles, to show a statement's false, you just have to come up with one counterexample. And you start drawing some equilateral triangles, and I think you're going to start thinking, gee, these all look similar. Well, are they similar? Well, the angle measures are 60 degrees for all of these. And in fact, all of the angle measures are 60 degrees. So you can prove any two similar triangles, any two equilateral triangles similar by the angle-angle rule, and you're just basically done with it at that point, okay? There are other ways you could do it though. You could certainly check to see, if you had a 2, 2, and a 2, and a 5, 5, and a 5, for example, you could check for this side-side-side similarity rule. There's a 2 to 5 ratio between these sides, a 2 to 5 ratio between those sides, 2 to 5 ratio between those sides. Those two triangles are similar. Okay, if I came over here and these are each 7, I've got a 5 to 7 ratio, 5 to 7 ratio, 5 to 7 ratio. You can see the side ratios are always going to be the same between any pair of sides. So they'll be similar by the side-side-side rule, by the angle-angle rule, and technically the side-angle-side rule, you could get a ratio and an angle and then another side there as well. So lots of different possibilities for that one. All right, our next example. True or false? Two triangles are similar if one has angles measuring 40 degrees and 30 degrees, and the other has angles measuring 30 and 110 degrees. The really important thing here, make sure that you're actually trying this scenario, okay? Make sure that you're actually drawing some triangles. So I'll kind of draw some triangles here. I've got angle measures of 30 and 40. So let's do a 40 and a 30. Fill in the missing angle because you don't know what's going on here. Those add up to 70, so that's going to be a 110. Okay? The second triangle, notice, we have a 110 here. It's a 30 and a 110. So we're going to have a 30 and we're going to have a 110. Those add up to 140, which is going to force this other angle to also be 40. Okay? So those two triangles are going to be similar by the angle rule. But again, you had to check all of the angles to be able to tell them. All right, next we want to find the geometric mean of 2 and 6. Remember, geometric mean, very simple to find. For a geometric mean, you're just going to take the two numbers and you're going to put them on one diagonal. So they're either the means or the extremes of your proportion. You've got the same variable on the other diagonal. Okay, so in this particular case, if I cross multiply, I'm going to get x squared is equal to 12. Okay, that means x is the square root of 12. We're going to focus on simplifying radicals in the next chapter. So you might remember from class, this is the square root of 4 times the square root of 2. Sorry, the square root of 4 times the square root of 3. It's going to simplify down to be 2 radical 3. That's the best answer. Radical 12 for right now is fine. A lot of these are going to be whole numbers, but they don't have to be whole numbers, and this one also. Okay, the next one here, the true-false statement, all rectangles are similar. Again, I'm thinking about this from the standpoint of trying to come up with a counterexample. On the surface you think, oh, I have the angle-angle rule, I can use that, they all have right angles. But be careful about that because the angle-angle rule is a triangle rule. And we didn't discuss similarity rules for rectangles other than just, for any shapes, all corresponding sides and all corresponding angles have to be proportional. We didn't come up with anything other than that. So I would flip this on its side. I would say, can I make two rectangles that are not similar? Okay? And of course I can. I can have kind of a long, thin rectangle like this, and I can have a not very long, thin rectangle like that. Okay? Those are definitely not dilations of each other. So be careful there because, again, there's no angle-angle rule for shapes that aren't triangles. That is a triangle-specific rule. Don't apply it in other places. You need to try and see if the relationship's going to work. Our next statement says that two rectangles are similar when the ratio of their sides is the same as the ratio of their areas. We've never discussed this, okay? Remember, this is a math class. This is not a guessing class. We literally have no idea, which means we need to try and we need to see what happens. So let's say we have similar rectangles. First of all, you have to think about what would happen to have similar rectangles. Their sides would need to be in the same ratio. You could think of one as being a dilation of the other one. So maybe if I have side lengths of 2 and 5, maybe I could triple the side lengths and make that 6 and 15. Something like that, okay? So make an actual example. And let's just try it and see if it works. If it doesn't work, we know it's false, and we've got our counterexample. If it does work, we probably need to delve a little bit more deeply into it and see what's happening. So in this case, the area is 10. In this case, 6 times 15 is 90, okay? The side ratio here is 2 to 6, which simplifies down to 1/3, okay? Sometimes we call that the scale factor between the two sides. And by the way, 5 and 15 also will have the scale factor of 1/3. They will all simplify down to be the same thing. Notice the area ratio here is 10 to 90. That's 1/9, okay? Areas are measured in square units. Sides of shapes are measured just in regular units, inches, centimeters, feet, that sort of thing. There is no relationship between the ratio of sides of similar shapes and their areas, okay? And we're going to see the same things get applied to volumes down the road as well. Volumes will not be in the same ratio as the ratio of sides, even if shapes are similar. All right, for this next problem, we're told that these lines are parallel, and we're told to fill in the proportion here. The proportion tells us that DE over AE is equal to BC over something, okay? I would suggest trying to figure out what the pattern is on the left and then continue that pattern on the right. So if you notice here we have DE, which is a lower part here, over AE. AE is the whole. So we have the lower part over the whole. I'm going to label that lower over whole. That's my ratio, okay? So on the other side, notice we also should have lower over whole. We have lower, and then the whole there would be side AC, okay? So figure out what the pattern is and fill it in. All right, we have the same diagram here. We have a little different relationship. This time it says that AD over AE is equal to something over CE. So same kind of thing, trying to figure out what the relationship is. AD is this upper segment here. AE is the whole. So it looks like we have an upper side over the whole. AD over AE. On the other side, notice they didn't give us like an upper and a whole on the other side. They give us something involving side CE. CE is down here. This is not a side splitter relationship. This is actually a full side of a triangle. It's not a partial side. It's not a side that's being split, okay? This is a case where you may kind of want to go off to the side and draw the two triangles separately, okay? You've got this upper triangle here, and you've got the bigger triangle. And the upper triangle is ABD, okay? And the big triangle is ACE, all right? Let's see if we can figure out what the relationship is looking at one triangle compared to another, since this isn't a side splitter. It's AD over AE. Okay, notice that's a small side to a big side, okay? So we're comparing corresponding parts of two triangles, a small to big comparison. So it's AD to AE, and notice it's a small to large, BD to CE. BD ends up being our missing segment there for that problem. All right, the next one here. We have 8x equaling 5y, and we want to find the ratio of x to y. You can do this a couple of different ways. If this was on your Algebra 1 final, you would probably just manipulate the statement. Multiply and divide x to y. We want x over y, which means I want x in my numerator, which it is. I don't want to have 8 here. X to be multiplied by 8, so you can divide by 8. And that would give me x equals 5y over 8. Remember that I want x over y. That would be x divided by y. So notice right now y is being multiplied by 5. Okay, we could divide this side by y, divide that side by y. The y's cancel, and we would have x over y is equal to 5 over 8. Okay, great way to do that. Doesn't require any geometry. All right. Now your book has made the point that cross products of a proportion are equal. So you could look at this as a cross product relationship. Okay, notice you've got a product equal to another product. And that's an idea that's been hammered again and again and again in this unit. A product equal to a product, those could be cross products of a proportion. Okay, so I want x over y. Why not go ahead and fill that in and just figure out where things need to go in my proportion to get that cross product. So x needs to be multiplied by 8. Y needs to be multiplied by 5. And you notice we get the same ratio here that we had in the previous example. So either one is fine. Okay, in this next example, I'm given some triangles here. Notice that we've got vertical angles that should be congruent. We've got these angles that should be congruent. These triangles are going to be similar by angle. So I really just need to figure out how I can set up a proportion here. I don't trust these diagrams when the two triangles are in different positions. Okay, I really encourage you to draw them both in the same position. Okay, so I'm going to leave that top triangle the way it is. Basically, we've got something kind of like this with this angle, and we've got that side of 6, and we've got that side of 9. Okay, this triangle is flipped upside down, and this angle matches with that angle on that side. So when we flip this over, it's this side is basically going to flip up to here. It'll be right there. The 4 is paired with that angle. Okay, and then the side that they want us to find is paired with the angle that's not marked. Okay, so you'll notice I have these two sides of this triangle. They match up with these two sides of this triangle. We have enough information now to be able to set up the proportion. Okay, so you know, you could do something like left over right equals left over right. You could do 6 over 4 is equal to 9 over x. Okay, you could cross multiply there. You'll get 36 equals 6x. And x is going to end up equaling 6, okay? But just be very careful. Make sure you have corresponding parts matching. This example is all about having corresponding parts match up correctly. And if you notice here, the diagram, not really drawn to scale, that's going to be a bit of an issue. This similarity statement is going to be really important. BET is similar to QCR, okay? And that's going to tell me what angles match with which angles, okay? So I'm just going to very carefully draw everything in the same setup. So BET needs to match with QCR, okay? So BET, QCR, okay? And just label everything accordingly. So BE has a length of 16, looks like. ET has a length of 15. TB has a length of 18, all right? And then this other triangle over here, we only have two sides. We have CR, which apparently my diagram is going to stay where it is, and QR, which is going to stay where it is. Okay, so notice we have these two sides. They need to match up with these two sides. 16 isn't needed. I'm just going to get it out of there so I don't match it up with the wrong thing. And we should be able to set up a proportion. We could do a scale factor here. A side of 15 matches up with the side of 20. Okay, so that's a left over right equals left over right, 18 over x. And you can cross multiply here, you get 15x equals, I think, 360. You might want to simplify this down if you're trying to do it by hand. You could simplify 15/20ths down to a scale factor of 3/4. Every 3 units in one is 4 in the other. Now you can cross multiply. 4 times 18 is actually going to be 720, okay? 720 is going to be equal to 3x. And 72 divided by 3 is actually 24. So x is going to be equal to 24 here, and that's our missing side. okay? And again, I think that can be very hard to see, although you can see some other patterns here. For example, if you divide, there's a 3 to 4 relationship here, which means this is 3/4 of this. This should be 3/4 of that. You can notice here, if you divide by 3, you get 5. And if you multiply by 4, you get 20. If you divide here by 3, you get 6. And if you multiply by 4, you get 24. So you can see those division and multiplication relationships if you look for them. But you've got to match the corresponding parts up first before you do that. All right, some of these problems are going to ask me to solve for multiple things. This one has both an x variable down here and a y variable. Be careful, we've got a capital X here representing a point. We've got a capital Y here. The sides are being represented with lowercase x's and y's, which I agree is a little bit confusing. All right, I'm going to focus on x first. It's first alphabetically, and I noticed something. I have a side splitter set up here. Notice that this side is parallel to this side. So this part of the side is going to match up with this part of the side is going to match up with that part of the side. We can set up a side splitter theorem proportion very easily there. So 8 over x, I'm going from top to bottom. Always good to label. 8 over x is equal to 20 over 15. That'll work out great. Again, if you're trying to do it by hand, you might want to simplify this. That's 4 over 3. And if you simplify that down to 4 over 3, you should get a real quick calculation here. I believe that x is going to end up equaling 6 when you solve that, okay? So that's your x variable there. Let's come back and take a look at y. Y is going to look a lot like one we saw just a couple of problems ago. Notice y is not one of the sides being split. That is a full side of the big triangle. It corresponds to the side of 10, which is a full side of the smaller triangle. Again, I've got a triangle inside a triangle, and I'm not looking at parts that are being split. I would look at the full triangles, okay? Draw your big triangle here. We've got a side length of, in fact, I don't even need that. This is the main triangle. We've got a side length of y, and I've got all the information about the parts of these sides, so I think I'm going to use this upper side here, although I could use the answer that I had from the previous problem down here, but I think this side will give me everything I need. So I've got a full side of y, and I've got a full side of 28 for that triangle. And then for the inner triangle, I'm noticing here I have a full side of y matched up with a small side of 10. So it looks like a big triangle with a small triangle comparison. We've got a big side of 28 matching up with a small side of 20, okay? And you might even notice there's a 2-to-1 ratio between the two parts here. So there should be a 2-to-1 ratio there as well, which would make y 14, okay? If you wanted to be a little bit more careful and set up an actual proportion here, we can do corresponding parts. We've got a scale factor of 28 to 20 from the big triangle to the little triangle, and that would be equal to y to 10 from the big triangle to the little triangle. 28 over 20, if you divide these both by 4, you're going to get, it's going to be 7/5 actually, if you simplify that fraction. And at this point, you can cross multiply. You're going to get 70 is equal to 5y, and y is in fact going to end up being 14. All right. So a couple of different ways you can do that, but I do think if you notice that there's a 2-to-1 ratio here, you're going to get a 2-to-1 ratio there. Remember, the ratio from triangle to triangle will be a consistent ratio. The ratios of the sides within the triangles will have their own consistent ratio as well. You can use either one of those. All right, this next one can be pretty challenging. We've got a triangle inside a triangle, but if you notice, this side is not parallel to this base. And so on the surface, I'm thinking this is not going to be any of the types of relationships that we've talked about. But if you look more carefully, they do tell you that this upper triangle here is similar to the big triangle. It's a case where they flipped it around inside the triangle. Imagine if I flip this over, this side would basically cut down like this, and it would end up being parallel to the other side, okay? However, do you have to be able to visualize that? Not really. This is a similar triangles problem. Draw the two triangles separately, everything should work out great. So I'm going to take the little triangle here, and I'm going to turn it in the same position as the big triangle. So that might look more like that. The little side, so notice I've taken this triangle and I've flipped it over, okay? So this short side of 9 is going to be right here. This longer side of 12 is going to be over here, okay? And the problem wants me to find, they want the length of ED, so I'm going to mark ED with the variable here. Actually, ED is already labeled with the variable, okay? The big triangle, those are the only two sides I've got on the little triangle, okay? So really, those are the two sides I care about in the big triangle as well. The big triangle, the side of 12 matches up with the big side of 20, okay? This short side of 9 matches up with this big side here. You need the whole thing, okay? That whole side is 12 plus x, okay? And so we can do some kind of a proportion. We can do a scale factor from the small shape to the big shape. 12 over 20 would be equal to 9 over 12 plus x, okay, comparing corresponding sides to corresponding sides. Again, you may want to make the calculation a little bit easier on yourself. These are both divisible by 4. If you divide this by 4, you end up getting 3/5. Okay, and now you can cross multiply and it should work out pretty nicely. 9 times 5 is 45. That's going to be equal to 3 times 12 plus x, which is 36 plus 3x. Okay, 3x is going to be equal to, is that 9 when you subtract? So it looks like x is going to be 3. Okay, and if you go back and check, 12 plus 3 is 15. 9 over 15 simplifies down to 3/5. This other fraction we had before simplifies down to 3/5. So that missing side there is 3. That's a tricky problem. It's tough to see unless you're told that those triangles are similar. Okay, this situation can be a little bit tough for people, but I think we had a homework problem earlier in the chapter that involved this concept. Notice that all three of these triangles are right triangles. We've got a right angle here, we've got a right angle here, and we'll have a right angle over here. The triangle on the right shares this angle with the big triangle. So the triangle on the right is similar to the big triangle. The triangle on the left shares this angle with the big triangle. And they both have right angles. So the little triangle on the left is also similar to the big triangle. Okay? If any of those triangles are similar to any of the others, they'll all have the same angle measures. That would force all three of these triangles to have the same angle measures, which means all three of these are going to be similar. Okay? Very simple then, once you make that realization that all three are similar. You've got a little right triangle, a middle right triangle, and a big right triangle. Draw those three right triangles. 2 of them should match up, okay? And so that's usually how I'm going to approach this sort of thing. So basically I'm going to have a little right triangle, I'm going to have a middle right triangle, I'm going to have a big right triangle. Those are the 3 pieces that make up this original diagram. The little triangle has a short leg of 2 and a hypotenuse of 3 radical 2. Sorry, a long leg of 3 radical 2. The middle triangle, which is represented here in the diagram, has a short side of 3 radical 2 and has a long leg of x. Okay, the big triangle, we only know one side. The big triangle's hypotenuse is x plus 2. Okay, these 2 triangles both have the legs matching up, okay? We don't have enough information on that third triangle to make a proportion. So, basically we match up the proportions between these triangles and we're done. We could do 3 radical 2 over x is equal to 2 over 3 radical 2. So I'm going from the little triangle to the big triangle. You could do height over base equals height over base. Lots of different possibilities. If you cross multiply, be careful here. You're going to get 3 squared, which is 9. Radical 2 squared, which is 2. 9 times 2 is 18 equals 2x. And x is going to end up equaling 9. That's all you have to do. This is almost an identical setup to the previous one. Notice we have 3 right triangles there. The triangle on the right shares an angle with the big triangle, and they both have right angles. So the triangle on the right is similar to the big triangle. The triangle on the left has a right angle, and it shares this angle with the big triangle. So the triangle on the left is similar to the big triangle. As a result, all 3 are similar to each other. So I'm just going to draw the 3 similar triangles. We've got a little right triangle, a medium right triangle, and we have a big right triangle. Sorry, I overlapped that just a little bit there, but we'll make it work. The little triangle, we have a short leg of 2 and a hypotenuse of 4. The middle triangle, we just have the long leg and its x, okay? The big triangle, we have a short leg of 4, and we have a hypotenuse that can be represented as x plus 2. Okay, so sorry, this is not the best picture in the world, but if you notice, this triangle I have the short leg and the hypotenuse, this triangle I have the short leg and the hypotenuse. We should be able to make proportions with those 2 triangles. Okay, so my proportion, I can do 4 over x plus 2 is equal to 2 over 4. Okay, and you might even notice this is a 1/2 ratio here. Basically this is going to need to be 4 over 8 to be equal to 2 over 4. But you could cross multiply here. You get 2x plus 4 is equal to 16. And if you subtract 2, you're going to get 2x is equal to 12. And x is going to be equal to 6. All right, we have our final problem. Let's take a look at it. We're told that AB is 15. So that's this thing right here. AD is 18, which is the side length down here, and BD is 22. We want to find the length of BC. Okay? I do not love this setup. I tend to like to draw this turned a little bit differently. So I'm going to take my triangle and I'm going to kind of rotate it around. I want to draw it more like this with my angle bisector up here. Okay? So my angle bisector is here at vertex A. Okay? So D is going to be this thing here, C is going to be this, and B is going to be that segment right there. So if we go back and look at the original, AB is 15, so that's 15. AD is 18, BD is 22, and we're trying to find BC, which is this thing right here, all right? The big thing here, this is the angle bisector relationship. These triangles are not similar. Really important thing to know, okay? No reason to think that these 2 guys are similar, okay? But remember, the angle bisector of a triangle divides the left and right-hand sides in the same ratio. So I like to see that angle bisector cutting the triangle in half. And we should be able to see the ratio of this right-hand side should be the same as the ratio of the left-hand side, except they didn't give me this segment, they gave me the whole side, okay? Very simple, you just need to recopy it. Something's gonna happen again and again. If the whole side is 22 and this side is x, I can label this side as 22 minus x, and then I've got everything I need for my proportion. So 15 over x, the ratio on the right-hand side is gonna be equal to 18 over 22 minus x, and you should be able to cross multiply and solve. This can be a little bit ugly, okay? So we're going to get 18x is equal to, it's going to be tough, let's see, 15 times 22, let's see, 15 times 20 is 300. So it looks like that's going to be 330 minus 15x, okay? And we can add 15x to both sides. It's very conveniently going to give us 33x is equal to 330, and as a result, x is going to equal 10. Okay, so a pretty challenging problem, but again, really just on the calculation end. Otherwise, the angle bisector part is very straightforward. But you do have to remember, sometimes you're going to have to label the parts that you want because you weren't given those parts.